Let's demo the insertion into a heap. Remember, the heap has two properties that must be maintained before the insertion or any operation is complete. The structural property, where we have a complete binary tree, and the heap order property, where any node should be smaller than all of its descendants. So 15 is smaller than all of its descendants. 25 is smaller than all of its. Same with 16. So we need to maintain these properties before we're finished inserting the number 17. We will always maintain the structural property first. So when we're going to insert 17, we'll have a placeholder, if you will, to keep our structural property, our tree, complete. Okay, once we have 17 in here, we'll have a placeholder for 17. We're not actually going to insert it. We'll find its real home momentarily, but we need to keep the property of having a complete binary tree. So let's say this is a placeholder for our node 17. So if we were to place 17 here, this would violate our heap order property because 40 is not less than 17. So what we will do is percolate this hole up and move 40 down here. Place 40 here. And does our new home for 17 violate the heap order property? Well, 17 is less than 25, so this is still a violation. So we compared 17 with the potential parent, 25, and we'll have to percolate this hole up and move 25 down here. Does 17 belong here? Well, does it violate our heap order property? That is 15 less than all of its children? Yes, it is. So we found the new home for 17, so let's go ahead and put 17 in its new home. Thus, we've finished our insertion, and 17 is now the left child of 15. Now, what is the runtime for inserting a single object into our binary tree? Well, the worst case is order log n. Why is this the case? Because what is the height of our tree? The height of our tree, since it's a complete tree, almost perfect, not quite, but it's a complete tree, the height of our tree is of order log n. So the most number of compares that we will do is log of n, log base 2 of n. Let's examine how the code works from our author. Okay. If our array is full, okay, which it isn't, we have space for it, we'll just resize the array and copy the elements into a new array that's twice as large. So we're going to invoke this method with the object, an integer object here, 17. And what we'll try to do is find a new home for 17 and maintain the structural and heap order properties. So what the code does is it creates a hole for our next object. So it pretends that this is the hole, and we're going to then move into our position in our array the number 17, or our object 17. Since it's empty, it's kind of a placeholder position. So we'll just go ahead and find a temporary holding spot for 17, and then what we have to do is figure out where the heck is 17 really going to live. So we're going to percolate this hole up until we find the correct position for 17. Before doing so, let me represent the indices for each of these objects in the tree. So 15 is in position 1 in our array, so I just labeled the node in our binary heap with a 1. 25 is in position 2, so position 2 here in red. Now we need to find a new home for 17, so the for loop right here is going to do that. Since 17 is less than 40, we're going to keep percolating this hole up and moving the node down until we find the new home for 17. We moved 40 down. Does 17 live here? Well, we moved 40 down. Let's go ahead and update this in our array. We moved 40 to our last position in our array, and then we come back into our for loop and we say, hey, 17, are you less than 25? Well, it is, so we're going to percolate the whole up and move 25 down. Let's update our array. 25 is moved from 2 to position 5. And then we need to determine, should 17 live here? So our code says 17, are you less than your potential parent? Is 17 less than 15? No. So we fall out of our loop and we go ahead and assign to this hole, okay, the value of array position 0, 17. So 17 is now in position 2 in our array. Again, okay, what is the runtime for this? How many compares did we do? At most, we'll do 1, 2, 3, our for loop, the height of our tree comparisons. So the runtime is big O log of n for a single insertion into an already existing binary heap.